we're going to continue on in this video to discuss line and curve fitting. If you want to get some more information about line and curve fitting, the 15th chapter of the textbook is fabulous. So if you go to the Stormy Attaway textbook at the library, you'll find in chapter 15 lots of great material about it. Okay, so line and curve fitting, very common thing. Many of you have already done it in Excel or one of these other programs, and it's super useful for doing basically anything with respect to visualization of measurements. You'll often do curve fitting of linear or nonlinear curves to the data, and often you need to infer results between data points, information that maybe wasn't collected originally, but you want to find out between two different measurements what was going on, and that's referred to as interpolation. And sometimes you need to also infer results based on the data that you gathered, but for information that is either maybe to the left or the right or above or below the measurements that you took. So they would be outside of the range of the data points, and that's what we refer to as extrapolation. So what's typically happening is that you've got some measurements that have been taken, say, of, let's see, temperature in degrees Celsius versus maybe day of the week, okay? And so what you'll do is you'll take a temperature measurement on one day of the week, and then there'll be another temperature measurement another day of the week, and then another one there, and then halfway through the day you take another temperature measurement there, and etc., etc. You take more measurements, okay? And afterwards what you want to do is figure out what the trend was for these temperature measurements over the days that they were taken. And so you try and fit a line between these data points. Pardon my crooked line right there, but that's effectively what we're trying to do. You're trying to fit this other line to all these individual data points as best as you can. And that's effectively the goal of what we're trying to do. Now, if you have data points that were taken, so you have original points that were measured, okay, and you fit a data point on there, or sorry, a line, you fit a line to these data points, you can use this newly defined line, okay, so this is the fitted line. So this fitted line allows you to then calculate, you're going to calculate other imagined data between data points that weren't actually measured, but based on this fitted line, you can calculate using the equation of the line points that could have existed between these other actually measured points. If you are outside of the range, so in this case, my range basically ends there and there, and if I wanted to infer data outside of that boundary right there, like this data right here, I want to know what happened there, then I would calculate using that line the data point that would exist at this point in time or along this in this area right here, and this is extrapolation. So we have extrapolation and we have interpolation over there. So to compute the best fit line, effectively what you typically do is try and find a straight line, okay? And we can write the straight line as y is equal to a plus bx, or in high school you might have seen y is equal to mx plus b. We just rewrote it slightly differently, where this part is right here and that is right there. So we've named the variables a little bit differently, but effectively this is your x-axis value, that is your slope, that's your x-axis, that's your slope, and then this is the y-intercept, that's the y-intercept right there. So we've just named it differently, but you've got your intercept and your slope. Now, it turns out that one of the ways to compute a straight line that is a best fit is to use two equations, one to determine b and one to determine a. Let's review what a and b were again. So a is the intercept and b is the slope. So this is the intercept, and that's the slope. And by taking a look at the data points that are defined by x and y values, each of these data points is defined by x and y. If we do calculations based on average y and individual x values, and average x and individual x and y values, and then you divide by the number of data points, so n is the number of data points, and you have an average value of x squared, and you've got this summation right here of all the individual x values squared. You do these calculations, and you can determine what the values for A and B are that best fit the data that you have. There is a way to calculate these, or to come up with or derive these equations, and I'll show you how to do that in a second here. But first, what we need to do is talk about something called residual error. And effectively what residual error is determining the difference between the measured values, so this measured value, and that measured value, and that measured value, and that measured value, and that measured value, and comparing it to, whoops, let's change the color there, like this. So we have this equation that describes the best fit line. I'm going to highlight it right here. This is the best fit line. Not quite a straight line when I draw it. Okay, that blue line right there. And what ends up happening is that you're trying to calculate the distance. Whoops, let's go back to that red. The distance between each of these individual data points and that line. And what you want is to have this residual error, which is the difference between the y value for the actual data, this is from the data, and the calculated y from the fitted line. And you want to know what the difference is in y values. This is what's referred, this height right here is referred to as the residual error. And you want to make this as small as you possibly can for, on average, all of these residual errors. And that's how you come up with your best fit, basically. So the concept effectively was introduced by someone named Gauss, and what we're looking for is to calculate the sum of the squares of the residual errors Ri. You want to have the sum of these squared values, and that's equal to this particular equation. So R sub I squared is equal to Y sub I minus A plus BXI. That's that best fit, right? That's your original data. You subtract one from the other, and this is your residual error. And eventually what we want to try and do is make those values as small as possible by making the line the best possible line. You get this, you get the solution for this by doing a calculation of partial derivatives and finding out when the partial derivatives with respect to A and B are equal to 0. So the partial derivative of the equation with respect to A is equal to this, and we set it equal to 0 to get the minimum, because we know that in a function, when you have the derivative equal to 0, effectively you're looking at the minimum value of that original line. And we do it as well for the partial derivative of that original equation with respect to B, and we set that equal to 0 as well. Now, if any of this is confusing, you can't remember how to do these derivatives, etc., I absolutely and totally recommend that you go and take this equation right here, and in Maple, write it out, okay? And so do something like S is equal to, with a colon right there, S colon equal, and then write in your equation here, and then right click, and look for the option I think it's derivative with respect to, and then you choose what it's with respect to. So you can right click your way through the actual derivative process and get effectively that result. Okay. Anyway, once you set that up, you do a little bit more algebra. So we wave our hands, we say that we've actually done this, and then you get two equations. You get the first equation like this and the second equation like this that come from those two equations right here, 1 and 2. So you have two equations, and then you manipulate the information so that you reformulate or reform these two equations as matrices effectively. So your first row, your n, your summation, your a and b, and your summation yi is your first equation. So you see right here, that's sum y. It's right here. Your a and b, right there. Your a and your b, right there. Your sum xi is right here. And your n is right there. Okay, that's how you break it up into the matrix form. I'm going to erase that to make it a little bit more clear. And then you do the same thing for equation number 2. And if you see here, let me see, we've got our a and our b right there. So there's our b, there's our a. We have sum xi. There you go, there's your sum xi right there. Your sum xi squared, which is right here. And your summation xi and yi, and we find that right there. So we've reformulated it in terms of matrix form, and this is what you really need to do if you're going to be manipulating this in MATLAB. This effectively gives you an equation in terms of a and b so that you can solve for a and b. And this is similar to what was on that original slide way back when. I'm going to go back to it. Right here. Equation number 1 and equation number 2. Effectively, what we did is we calculated this or formulated this in terms of the matrix form. I'm going to go back forward again. Right here. And that's that formulation right there. Okay? So equation 1 and equation 2. All right, so all that to say that built into programs like MATLAB and Excel, you effectively have this process going on. Now, if we're going to do line fitting examples in MATLAB, here's what we basically do. We've got data, and data is made up of x values and y values, x values and y values, and we type these into MATLAB. So we have these data pairs, -4 and -37, 3.7 and 38, 0 and 0, 2.5 and 29, etc., etc. And these are our data points, okay, of x and y. From there, we want to know what are the coefficients for a first order or linear polyfit line, okay? And so we say, here is the data that we need, x and y, and we want a order 1 polynomial fit. We run this into polyfit in MATLAB, and effectively what you end up getting is two coefficients to describe the equation y is equal to slope multiplied by x plus 4.2564, which is the y-intercept. And so effectively you have your two coefficients applied to the equation. We now have an equation for a best fit line. Okay. Next, MATLAB provides not only this polyfit equation that allows you to get the coefficients, and here we're going to output the coefficients to a variable called coefs, and you can then take that coefficients variable, so it's basically in this case a pair of numbers, and we can feed it into another function called polyval. And what this will do is come up with the y values that correspond to the line that's been computed at particular values of x, for all of the particular values of x that we had, and it will calculate all of the y values along this new best fit line. So we've got 1, 2, 3, 4, 5, 6, 7 different values along this new line that we've created, and they've been calculated with respect to the coefficients and with respect to the x value. Now, if we want to calculate the residual errors, we can do that. And in that case, what we do is we use the same value of x in our polynomial fit, the same value of x that we had in our data, and then we calculate the difference between our y values from the original data, and we subtract all of the y values that are from the fitted line. And then we get effectively all of the errors per measured data. Next, you can then take the original data and you can create a new line that has interpolated values. So I'm going to highlight it here. In our original data, we had data points there and there and there and there and there, like that. And with this polynomial fit, what we can do is come up with interpolated values at very regular intervals and extrapolate it as well. So we got made up values that correspond to the best fit line at nice linear regular intervals, like that. And that all fits on the line that's sort of hard to see, but it's in there, like this. And so what we do is we end up defining the fitted values of x, the ones I had the little dots in pink there, defined using linear space from -6 to 6, and I wanted 20 different points. From there, I want fitted points on the y-axis, and those are determined from polyval using the coefficients that we calculated earlier and the x-fit values that we calculated right here using lin space. And then what we ended up doing was plotting, whoops, let me get the better color here, like this. We plotted the original data versus the fitted data. That's what we did right there. Now, next thing to talk about is what happens when you've got anomalous or sort of outlier kind of data. And depending on how this data is set up, it can provide a stronger or weaker effect to this best fit line. And we can talk about that in terms of leverage. Okay, so it turns out that in this particular case, what we've got is an example that highlights high leverage. And that's because you've got this point right here that really throws off the best fit line. Really, it should be closer up here, but because this data point is so anomalous, it's so way out there, it throws off the best fit line. Now, it could be that this is representative of something actually really happening in your data set. And a recommendation always, when you've got these outliers that are throwing things sort of in a weird way, is, if you can, try to repeat the experiments. Repeat or add more experiments. And you might see that in this section right here, the data is nice and linear. And then maybe there's some nonlinearity over here that gets affected by something, some environmental condition or something. And that really only comes out if you do repeated additional experiments to see if you can reproduce the events that lead to this. It could also just be sensor noise. There could be some silliness that's going on that is truly anomalous, and by repeating your experiments, you might actually be able to confirm that. So seeing these high leverage points that really throw off your line, they could be an indication that either A, nothing's actually wrong, or there could be actually something very different that you don't quite understand. So pay attention to those when you see them. Now, on the other hand, sometimes when you have these anomalous results, depending on where they find themselves in your data set, they might not have any effect or very little effect at all. And that's what we refer to as low leverage. So in this case, the best fit line, this one right here, and what would be sort of referred to as truth, the true line that really describes things, they're actually relatively similar. And so what you find is this anomaly right here doesn't really affect things too much. And that's what we would refer to as a low leverage kind of data point. Okay, so you will see in your studies in university lots of examples that are linear, that can be confirmed or characterized by straight lines. But you know what? In real life and in your sort of later courses, you'll see that a lot of things that happen are nonlinear. And every time you encounter a nonlinearity, the way you deal with it is very likely to be different than some other nonlinearity. Sometimes there's exponential components, sometimes there's discontinuities. There could be all sorts of reasons for that. In this particular case, we're going to start off with something that's nice and simple. Effectively, we're looking at an equation that describes cooling states. And so we can see here that the temperature is a function of the environmental temperature, some original temperature, and then some component with respect to a variable r and some time that affects things. All right. But this right here, this e to the power of negative RT, is nonlinearity. That's the source of your nonlinearity. Okay. Now, when you have nonlinearities, often you're confronted with a choice as to how to deal with it. And the choices basically boil down to this. Either you can try to shoehorn in a linear fit that won't look very good, or it's good for now, but you really should try something else. So you can try a best fit. It might not look good, but you can give it a shot. Really, one of the other, maybe often better choices is to change how your data is visualized in order to make it linear. And we often see this with logarithmic plots. The other thing to do is to come up with a more clever or insightful way of dealing with the nonlinearity, maybe by breaking up the problem into multiple sections where some is more linear than others, or to apply some filter or some other process that allows you insight into the nonlinearity itself. Maybe you have to go from a straight line to some other polynomial fit. Maybe you have to have a fifth order polynomial fit or something. And that's always dependent on the type of data that you're actually dealing with. So those are the three basic choices that you often are faced with. Okay, so let's imagine that you've got 20 measurements and you're trying to determine what this value of R is, okay? And the basic trend looks something like that. That's basically what you're up against. Now, this data set right here has been artificially created using this equation right here. So we've replaced the variables in the equation that you saw earlier with constants. And so we've replaced them in here and we've made up a value for R right there. And we've got a value T, and then we've added in some noise, some randomness. Okay, and that's what allows this line or these data points to be sort of a little bit noisy. Okay, that's what this randomness is for. And there's lots of different ways you can add in randomness, but that's what we've done right here. That's what that term right there is. Now it turns out that you can reformulate that equation right there in a way to isolate for R and T. And that's by introducing a natural logarithmic function that is a function of ratios involving temperature. Okay, that's effectively what you're doing right in here. Now remember, something else to consider, or something to always consider, is that when we talk about transforming nonlinear relationships, effectively what we're doing is we're doing manipulation, and we are going to be looking at the natural logarithm, but it's important to not get confused in MATLAB, because MATLAB refers to as the natural log as log, and the log base 10 as log 10. Okay, just important to realize that. So here we go. We've got a MATLAB script to transform this nonlinear relationship. And effectively what we've got is the natural logarithm log. In this particular case, that's how MATLAB refers to it. This is the natural log. It's not a typo. That's actually how you do it. And then you've got the equation where this is the ratio of temperature values that we were talking about earlier. That's the equation right there. We have data points that were defined in terms of t and u. Okay, so t is time and u are the data points that were plotted earlier. The coefficients will be calculated from t and u, and we're looking for a first order fit to that. From there, you determine that the coefficients come out of this. They get fed into a polyval function where you have your coefficients and your horizontal values, your t or time values right there. And that gives us our fitted values for u. All right. So then we're going to do a plot of time versus the original data. That's this right here. And we're going to compare it to the fitted data right there, or filtered or fitted or manipulated data. And from there, I'm just going to show you what that ends up looking like. Okay, so what we had was the original data, like this. Like that. And then there was a polynomial fit, and that's what that line in the middle was. Okay, so we've plotted these two things right here. Now, what's nice is that we have displayed this in terms of a linear graph. Because we have reformulated the equation, it is now linear. Now remember that the way that we've dealt with this nonlinearity is very specific to this particular data and this particular problem. Just because we've applied it to this particular nonlinear behavior doesn't mean you always do it this way with nonlinearities. It's always on a case-by-case basis. Okay, now if you sort of look at it from its linear perspective, or its original perspective, its nonlinear perspective, this is what it looks like. So you can see that curve right there. Okay, so effectively we've been looking at the same data, but without the linearization. And you can see that basically the fit is actually pretty good as well. Now, polyfit can be used to fit not just lines, straight lines, but also curves. And that's effectively what we're talking about when we have polynomials of any degree. Degree 2, degree 3, degree 4, etc. So here's an example of launching a ball into the air, and we're going to get ballistic flight. All right? Not flight, or not fight, ballistic flight, like that. So we're going to start with the time of t is equal to 1 second, and we need to figure out the measurement of the height of the ball. And we need to also find what the initial velocity was and the initial height of the ball was. And this will be with respect to extrapolation, because our measurements will be starting at 1 second. That's after the ball was launched, and we will have to go back in time to extrapolate what the original conditions were. Okay, so when we're doing polynomial fitting in MATLAB, we're going to create some fake data right here. Okay, this is referred to as like the oracle data, the data that that only a higher power would actually know. And so we've got this ideal data of defining y or height with respect to a gravity term, a velocity term, a position term, and random noise like this. So we have our height, y, our t time, and what we can see right here is that we've got, after 1 second, we're measuring the trajectory of the ball as it goes up to its apex and down to the ground. So we've got data in terms of time and y, and that's from that equation right there that we've come up with to create the data that is sort of quote unquote measured. So we've got this t and y, so our time and our height values, and we're looking for a second order polynomial fit. Okay, so a second order poly. We also will create a second set of time values, t2. They're defined as a linear space between time is equal to 0 and time is equal to 3, and we want 20 individual values between 0 and 3 seconds. We want a y fit that is related to these values of time based on the coefficients that were calculated for the best fit line, or best fit curve, okay, because it's not a line anymore. It's a second order polynomial. So the best fit curve using these coefficients, and we will get new values for a fitted series of y values related to T2. From there, we are going to take our original data, that's the measured data, and then we are going to compare this to the second order best fit. All right, and here's some equations for the coefficients themselves in terms of the gravity constant, the velocity constant, and the height constant y. So remember that we have time, we have y, we have this measurement, etc. We have these coefficients, etc. And that's not a third order. So we're looking at a second order right there. Okay. So what ends up happening is that I'm going to highlight the original data. So we have the original data there. Okay, like this. Those were our measurements that we took. Then what we have is an ideal condition, and that ideal condition is that line right there. That's based on that original equation that we made up, like this. And then, that's the ideal condition right there. And then what we ended up having was a polynomial fit, second order polynomial fit, and it created an equation of second order that was very similar, not quite, but very similar to the original quote-unquote measured values. And from the fitting, what we ended up getting was an estimation of the gravity term, an estimation of the velocity original term, and an estimation of the original height, which actually aren't that bad. They're off by just a little bit, just a couple of percent. Okay, but basically the other thing to point out is that all of the data that could be calculated in here, including the intercept conditions, are all based on extrapolations. Any additional data points that we calculate in here, between here and here, are for actual between measured values, and that would be referred to as interpolation as well. Okay, and there you have it, a summary of best fit lines and curves using MATLAB, and how MATLAB effectively comes up with its algorithm for determining how to make a best fit curve. And you can apply these to lines, as well as curves that are in second order, third order, etc.